Hello, my name's Peter Stones. I work for ESAB. I want to tell you about duplex stainless steels. Why are they so good? A little bit about their history, their background, the recent developments in new grades. And of course, we're a welding company, so we'll talk about how to weld them. So, what are duplex stainless steels? Well, the word duplex comes from the Latin meaning twofold. And what it means is it's a combination of austenite and ferrite. So we have these two magic properties, phases, they're called in steel, austenite and ferrite. We have austenitic stainless steels, we've got ferritic stainless steels. The clever part about a duplex stainless steel is that it's a combination of the two. And this combination, the resultant combination of austenite and ferrite, creates a fantastic material that is very corrosion resistant and is very strong. So the tensile strength is very much better than, say, a standard stainless steel. Okay. What you see here under a microscope, a picture of duplex stainless steel. The white areas are austenite and the black lines around them are the ferrite. So what we have is a 50-50 ferrite austenite balance. The composition of the steel, typically for duplexes, anything up to 25% chromium, 9% nickel and 4% molybdenum. Each of these alloys has an effect on the properties of the stainless steel. They're there for a purpose, but the duplex is not just because it has this combination of these alloys, it's the way that it's manufactured. And the way that it's manufactured is to make benefit of generating the austenite and ferrite balance. Looking a little bit into the history, it's fairly recent history. The duplex as a grade was only around since about the 1950s. This graph here, the line between 1970, the first generation were just not weldable. These grades of duplex were not weldable. So the second generation are all weldable. What we have on this graph here is this magic number called PRE, which is pitting resistance equivalent number. So you put the composition, the composition of the alloy into this equation and come out with a number. So the amount of chrome, molybdenum, and nitrogen. You come out with a number, and this PRE number is a measure of how resistant the alloy is to pitting corrosion. Pitting is a very dangerous, difficult method of corrosion because it's not really predictable. We see some photographs of the effects of pitting corrosion later on, and it's a good illustration of what happens basically. So you see the measure of PRE, we start off with these things called lean duplex. Lean duplexes were invented because they didn't have so much nickel in them. When nickel was really expensive, someone developed duplexes with not so much nickel. So these are lean duplexes that have got a PRE number below 28. Duplexes, this standard duplex is fairly common grade these days. The standard duplex has got a pitting resistance equivalent number of greater than 32. The super duplex needs a pitting resistance of 42. And then we've got this thing called hyperduplex. Now, hyperduplex has a PRE above 48. And the difference between these, the higher that you go up the scale, the more resistant these things are to pitting corrosion. And similarly, the stronger the material gets. So in terms of tensile strength, we've got a big jump from lean to duplex to super duplex, and then from super duplex up to hyperduplex. Okay, and I'll show you that later on. So looking at this PRE number, this magic pitting resistance equivalent number, in terms of, say, a standard stainless steel, a 316L stainless steel has a PRE of 24. So that, obviously, it's a stainless steel. It does have a resistance to pitting. But you see, on the same scale, compared to a standard duplex at 32, super duplex at 42.5, and this hyper duplex at 49. And the effect that that has is fairly well illustrated in this photograph here. So all of these test coupons have been submersed in this nasty solution, 6% ferric chloride at 80 degrees. So it's a reproduction of a G48 corrosion test, a fairly standard corrosion test for stainless steels and duplexes in particular. So you can see over on the left-hand side, we have a 316 stainless steel that looks like it's been very badly corroded. It's corroded on all surfaces, and these things are the pits. So these are massive holes in the surface of the stainless steel. And the thing with pitting is that, like an iceberg, underneath is where all the damage is. There's more damage below the surface beneath these pits. As you're going up the scale, we've got a lean duplex, so a standard duplex, 2205 standard duplex. You can see it's been affected, it's been corroded on all surfaces, and we've got the start of pits all over the surface. So compare that with SAF 2507. So this is a super duplex with a PRE of 42. You can see it's been exposed for the same amount of time, same temperature as the rest of the test coupons, and it looks like it's not been touched. So that's one of the reasons, that's a good illustration as to why duplexes were developed. So you have fantastic strength and excellent corrosion resistance. Mechanical strength, again, on the same scale, we're talking yield strength up the y-axis. So the 316, yield strength of 200. So compare that with, say, a super duplex that's got 550. Okay, so it's more than twice the yield strength of a standard austenitic stainless steel. Okay, again, this is why they were developed. The applications that they're used for make use of these particular properties. Okay. If we look at a micrograph of a weld, okay, so this is the fusion line, base metal over here. So this is a nice duplex material. You can see nice fine grains. It's a nice balance between the austenite and ferrite, nice grain size. As we get into heat affected zone, the grain size is getting bigger, but you've still got a duplex structure. You've still got a nice mixture in the structure. And similarly with the weld. The weld's obviously got bigger grains. This has been molten and frozen, but you've still got a nice structure. So this is what you're trying to achieve, okay, when you are welding duplex stainless steels. There are four things in particular to take note of. The first one being the joint preparation. Stainless steels, and the more highly alloyed that they are, the fluidity of the weld pool is not so good. So the design of the joint, it needs to be such that the root gap, for instance, is wider. This to allow the sticky weld pool to flow into the gap. If it's not taken into consideration, then there's a possibility of getting things like lack of fusion. You're not going to get the weld pool to flow into the joint. Shielding gas. We recommend nitrogen for duplexes. Nitrogen turns the ferrite into austenite, as if by magic. So there's nitrogen in the metal. As soon as you start heating that up, the nitrogen's going to want to disappear. So you need to put nitrogen back in. Nitrogen creates austenite, so it turns the ferrite into austenite. Very important. And I've got a couple of photographs that will illustrate that. Heat input. And interpass temperature, critical for high alloys, in particular duplexes. Some of the numbers are quite low, and again, I'll illustrate that later on. And then what are the effects if you heat it up too much, if you cool it down too quickly? Okay, so these two photographs illustrate the addition of nitrogen. So you've got a pure argon shielding gas. Okay, so in the surface here, none of the ferrite has turned to austenite. So this dark areas here are ferrite. That means that you've got ferrite properties here, which means not so good corrosion properties, not so good strength. So in effect, it's an area of weakness. Over here on the right-hand side, we've got a nitrogen in the shielding gas. You've got a lovely structure, austenite, ferrite, all the way right to the end, right to the fusion line. So this is a proper duplex. It's going to have all the properties of a duplex. Similarly, in the purging gas, same effect. If you don't replace the nitrogen by having a lot of nitrogen in the purge, then you're going to get these fully ferritic areas. So again, you've got a range here that is basically ferrite, not duplex. So you don't have the strength, you don't have the corrosion resistant properties. In terms of heat input, there are very strict recommendations on every grade. For instance, a standard duplex, we're talking a maximum of 2.5 kilojoules per millimetre with an interpass of 150. The hyperduplex, which is obviously more highly alloyed, we're talking a maximum of 1 with an interpass of 100. And yeah, basically, why do we do that? And this is the reason why. So this is a sketch, if you like, of a transformation diagram. So this illustrates the phases that the steel will turn into as it's cooling down. So if you're cooling down over a long time, there's time is on the x-axis and temperature on the y. So up in the high temperature, this is molten. This is the molten metal as it's cooling down. So this is the weld cooling down. The more time taken, and as you cross these lines, then this illustrates the phases that are going to be precipitated into the molten metal. So if you take too long to cool down, then you will dwell. There will be portions of the weld that will be at these temperatures for an extended period of time, and that creates problems. It precipitates these intermetallic phases in the metal. What does that mean? So we get in these sigma phase is the big nasty word that people have probably heard of. So these dots here are sigma phase. So these are basically clumps of ferrite that have been precipitated in amongst this metal. So you have points of weakness in amongst the structure of the metal. So this whole the whole weld is not going to be as strong as a proper duplex. Okay, how would you get too slow cooling? So it's got too hot. It's got too hot. So maybe the interpass temperature has been ignored, or yeah, the welder needed to get an extra pass in before he went home, so he ignored the interpass, which made the whole thing too hot, meaning that the dwell time, the cooling, was taken too long. Conversely, on the other side, too rapid cooling. So again, yeah, he wanted the interpass to be in the right region, so he cooled it very quickly with a hose pipe or something. You can see what's happened here. You've got massive freezing of the grains, so massive big grain sizes, with chromium nitrides being produced at these grain boundaries. So you've got nitrides and chrome depleted areas in the grain boundary. So again, this is not a proper duplex structure. This won't work. What you're trying to do is to have a nice middle of the road cooling to create this nice duplex structure. Okay, we do have troubleshooting tables for what's gone wrong in your weld. There are questions and answers if there's too much sigma, if there's too much austenite, too much ferrite, if you're having difficulty passing the G48 corrosion test, then all of these things are available if you request them. So in terms of applications, the applications for duplexes are fairly far and wide. Transportation is a prime example because of the strength. The mechanical strength of the metal means that you can reduce the thickness. So you get the same amount of strength from a reduced thickness, which means reduced weight. And weight is always something that's been chased in vehicles. Oil and gas. applications, oil and gas and petrochemicals. So there's a lot of chlorides in there. Duplexers are particularly resistant to chloride attack. So there's an awful lot of applications there. You can see we've got submerged arc welding, we've got an orbital TIG, but there are a lot of applications where the mechanical strength and the corrosion resistance of a duplex is primary and key. Heat exchangers, again, in an oil refinery, so there's chlorides, providing the temperature is not above 300 degrees, then again, it's perfect. And a couple of applications for architectural use. We've got the Louis Vuitton Museum in Paris and also this bridge in the UK, both of which use duplex stainless steel because of the strength. You can reduce the weight. This bridge in particular was able to be lifted in one piece, so it could be assembled off-site, lifted in one piece. Plus, both of these architectural applications, they don't need painting, they don't need maintenance. So the stainless steel won't rust, won't start looking bad and need painting. So in effect, it's a cost saving too. So that's all I have. I thank you for your attention. It's been my pleasure to do this. Please take note of my contact details and Mr. Tallarico's details. Should you wish to ask us any questions about duplexes, stainless steels, then we'd be more than happy to answer you. Thank you.